So there's no difference in the charge separated state, whether it comes from the Hall transfer or from the electron transfer. I'm not saying that those processes are identical. They're not. Of course not. They can have different reorganization energies, and all of these things can be different. But the end product, if you wish, is the same. Has the same picture. Okay. Then this was the introduction to the block junction. This summarizes everything. This is a standard kind of morphology picture, and the standard layout for the solar cell. And of course you have all your extra layers, as you can see here already. A number of years ago, Janssen had these beautiful pictures of a cross-section of a solar cell. At that time, at the bottom the glass, and then ITO, P.ESS, and OPV Pcbm, a very thin layer of lithium fluoride, and then the aluminum photoelectrode. If you look from the top, either the TM or the DFM, to this active layer, then you can see some kind of morphology situation. And then this, the last slide I had is that you can do all kind of funny stuff with OPV, not only flexible or whatever, but I think one of the really cute things that came out already a number of years ago, this is 2009, from Konaka, from a company. I think it's really interesting. The company was crazy enough to do this project, to make a photovoltaic wire, a conducting wire that gets its own electricity from the light. And that, I mean, that's really cute. They even made some kind of textile stuff with it. Yeah? Well, of course, it worked pretty well, but not good enough to be anything interesting. So this was then the last slide of that first presentation, where I want to remind you of what are the important processes in an organic solar cell. Where am I? Glasses. Okay. So then we go on. Fullerenes. So now this hour I will talk about fullerenes as the acceptors, because as I already told you, fullerenes are in all of the best organic solar cells. Whether they are small molecules, Moritz Riede, I understand you have heard all about it, C60, or if you have solution process, then you have to have some kind of a soluble C60 derivative, it can, for example, be Pcbm. Starts with C60. Why fullerenes? So the discovery of this plastic solar cell was with fullerenes as a very good acceptor, as a very good quencher. An extremely good quencher, and you had this photo-induced electron transfer with 40 femtosecond time scale. So you can also do that with other fullerenes. This is C60. There's one isomer of C60. This is C70, or well, this is not C70, this is a drawing of C70. And yeah, well, you know, sometimes you forget it. As my teacher said, that yeah, in reality it's much smaller than this. It's not much of a surprise to me anyway. So anyway, there's only one isomer of C70, and then when you go to 72, there's only one isomer of C72, and then one of 74, 76, then there are two of 76, three of 76. There are a number 4 of 78, there are a few of 80, and so on. And then when you get to 84, I don't think it's 84, look at that. You have 24 isomers on paper. But this is all computer generation. So theoretically there are 24 different isomers of C84. In reality, some people, you have people that actually do this. They try to separate and isolate and look at the different isomers of 84. And I think by now something like 8 or 10 different isomers of C84 have been analyzed. But it's so academic, we're not going to talk about that. Only 2 isomers, sorry, 2 fullerenes, 60 and 70. Because all of those you cannot even find in your mixture in reality. That you also cannot buy them. They're incredibly expensive. You cannot get them. So they're not useful. We only have to talk about 60 and 70. Okay, here's 60 and 70. See, 60 has the soccer ball, in the old-fashioned soccer ball, which was made of hexagons and pentagons. And here is the presentation of course, the perfect sphere. I think the most symmetrical molecule that has ever been made. And here's C70. I did something funny here. I made this red and I put rings in there. Why did I do that? Because I want to teach you that this stuff does not have rings in hexagon, and this stuff has rings in these hexagons at the equator of the molecule. What do I mean here? Maybe, hopefully, most of you know that if you draw a 6-membered ring and with this ring in there, it means benzene, and we say that the orbitals are completely delocalized over the ring. So people say you have a ring current. Of course you don't have a ring current unless you put it in a magnetic field. But anyway, so I do not draw that benzene structure here, and I draw the benzene structure there. And that is for a very good reason. That is, that this is probably one of those first molecules where you can really draw cyclohexatriene instead of benzene. This is not a benzene ring. While only these hexagons that are on the equator of C70, they have some benzene-like character. They are more like benzene. So these are aromatic rings, if you wish, and these are not aromatic rings, if you wish. And that means that this stuff is also quite reactive with the double bonds. These double bonds are not very reactive. The reactive double bonds are here at the north and the south pole. And it's maybe not so surprising, because that's where the system is most bent. And so there's more strain, so it's more reasonable that you have more reactivity here and there. Okay, anyway. Voila, Pcbm. Pcbm. P-phenyl, C61, C60 plus 1, 1, 2, 3, 4. Butyric acid, methyl ester. It's a very bad name for a chemist. I gave it that name, I admit, but it's a really lousy name. But it worked like crazy, didn't it? Okay, this doesn't work. Yeah, so I brought some really old slides, and then I had a period. Everybody has this period that he or she starts making presentations with a black background. Now you know why you should never do that. Okay, never make presentations with a black background. But I thought it was sexy. It was Okay, so this is a synthesis of Pcbm. You take this, what this side group has to be, but it has a very reactive piece, a total hydrogen. This is not reactive yet, this is a total hydrogen. But then we put some base and we make a diazo compound, which is very reactive. We blow off everything except the 2 nitrogens. And that reacts with the double bond of C60 with this double bond of C60, and it gives you this this is a 5-membered ring. It's difficult to see if you don't know it. It's a 5-membered ring with those 2 nitrogens in that ring. And on this one carbon is this butyric acid and this phenyl group. And then something really funny happens. The nitrogen goes out, and nitrogen gas is N2. It goes up, and when you heat it up a little bit. And this is what happens during the reaction. And then something really strange happens, because this double bond was between 2 6-membered rings. And now here I have the nitrogen out, and now I get this bridge over a 5-membered ring and a 6-membered ring with nothing in between. So it's incredibly complicated. And then this isomer, if you either shine light on it, or you make it hot, or you put strong acid, or you do electrochemically, or probably when you laugh at it, it goes to another isomer and it forms what everybody would expect it would form. So this chemistry is extremely complex, but the good thing is it works 100%. So, I mean, it looks on paper it's very complex, but the reaction goes very efficiently to this product. And this is the addition of this diazo, the compound that you made that I just told you, and it gives you this 5-membered ring, and this is all about. You can use other compounds that look very much like it, and you make the aza fulleroids, and you can also use other compounds, and then you get the famous fullerochlororidines or Prato adducts named after Maurizio Prato. So here, immediately, I bring you methanofullerenes, aza fullerenes, or fullerochlororidines, and most of the fullerene derivatives have this shape. There are a few other ones. And I will not bother you with all the chemistry. It's extremely complicated, but let's forget that. So let me say, this is how you make Pcbm, and you can we can make Pcbm on multi-kilogram scale. There's no problem. So all the problems have been solved, all the nasty solvents are out, and so it's ready to go on ton scale. There's no problem. If somebody says there's a problem with fullerenes availability or anything, it's simply not true. Yeah?
Does that apply to C70 also?
I can't hear you.
Is that just C60 or C70 also?
Pure C70 is much more expensive than pure C60, and as I told you, if you can use a mixture of 60 and 70, it becomes much cheaper. So that is the way to go if you really want to go very, very large scale. And most polymers tolerate that. This is not what you should use in your academic research. Just use pure 60 or 70 or so. And once you start a company, then you come back and we will talk. Okay, now I give you the story of Pcbm. Because I have many friends in fullerene chemistry that were extremely frustrated by the fact that the very first compound that was used as a fullerene derivative is still there, no matter how many derivatives they made. And so they got jealous and angry and everything you become. Yeah? Of course, we have always told them that we were absolutely geniuses and we knew exactly what we were doing. So therefore it's time that I give you the real story. The real story started with Fred Woodall. I found a really ugly picture of him, so that's why I put it, because I gave this talk for him when he had his 70th birthday. So he looks like a croupier. But I don't know if you know these things, but this is how many publications every year, this is how many citations every year. And I promise you, if you have a Hears index of 89, you have 640 papers and 37,000 citations, you are a real big shot. This guy is really good. Yeah? We always talk of Rene Janssen and Sarah Saracchi, we always say, well, we play football, but you know, those guys, different league, different league. So anyway, so this is pretty interesting. But now I am proud to show you the same numbers for Pcbm. And this is Pcbm. It's a little bit more promising than Fred Woodall because it goes up like crazy. You see that? And by now, this year, the Hears index of 60 Pcbm is 95, and there are 45,000 citations to Pcbm. And so this is what I smacked him in the face, that his, our baby is more popular than himself. So that's Pcbm. So there are, why and how did this happen? Well, it's very simple. I came to Santa Barbara as a very old postdoc. I was 39, and but he accepted me. And Fred said, "So what are we going to do?" Well, he said, "Well, I had another Dutch guy just before you. He left. He went back to Holland, and he made the first water-soluble fullerene. And why? Because fullerenes can stop, or at least, let's say, inhibit HIV." So this is has nothing to do with what we always do. This is all molecular electronics and organic electronics. But he had stumbled into that. And so he said, since you're also Dutch, I think you should just follow the class. and you should make more water-soluble fullerenes to stop HIV. This was 93, and I promise it was very important and very big at that time. So close to San Francisco. I mean, and there was collaboration with San Francisco universities and medical centers. So it was a real hot issue at the time. So this was the molecule that Sibesma made. And water soluble because you have this acid and this amide, a little bit like protein kind of groups on both sides. So it becomes so-called water soluble. It's not water soluble at all, but it's somewhat water soluble. Whatever. It's soluble in solvents that you can mix with water. Okay, anyway, first up. So he said, you do that. And then they said, yeah, but I said, no, but I know what you're going to do. Now you're going to make me make this molecule, and then the medical guys want that. They want to have a protein on it, and then they want to have a sugar on it, and then they want to have a hormone on it. That's how they want to try everything. So I propose we make one molecule, one fullerene derivative that we have in a bottle, and that we can use to put all kinds of side groups, a sugar, a hormone, a protein, whatever you like, I will put it on it, then I have less work. Yeah? So he says, that's a good idea. And I say, okay, so we want to have, when we do, is we want to have a fullerene and we want some other stuff on it. Yeah, okay, so then they said, I said, well, I just got my PhD on something which is kind of similar. This is adamantiladine adamantane 1,2-dioxide. Try that. And this is a very interesting compound because it gives light, chemical light. If you heat this up, you get light in the dark. Yes, chemiluminescence. And then, so I have put a side group on that and an active group which can blow off, so I can put any group on it. Doesn't that sound similar? So I said, you know what? I have learned that in immunology, if you have two molecules, and you want one molecule and the other molecule to behave as if they are still themselves, you should always put a 5 or 6 atom chain between. Don't put them too close to each other. Use something like 5 or 6 atoms. That's a golden rule in immunology. Yeah? So I said, okay, so first I know how to have that bottle with that stuff in there that binds to everything. Then you need to have this group. And look at that, 1, 2, 3, 4, 5, 6 atoms. You have to have about 6 atoms. That's why I did that during my PhD. But let's do the same thing with fullerenes. So we want to have C60 and we want to have 1, 2, 3, 4, 5, something. Okay? And then Fred said, no, that's okay. But then we're going to make a methanofullerene, because that's how we work here. And I promise if you want to make the methanofullerene and you want to have the chemistry okay, then put a phenol group there because of the simplicity of the synthesis. Just to make life easy. Nobody cares about the phenol group, let's just put that one. And then I said, okay, then we have everything, because now we have the molecule, then we have the molecule with an active group that we can have the target on, so we have this active group. Voila, the design of the bottle that was going to give all our medicine against HIV. Now I have to go back to the lab and synthesize this. And if you synthesize this, you don't synthesize this, all of this with this group. You put this group on at the end. Now I give you retrosynthesis. If you want to make this molecule in retrosynthesis, as we call that, the arrow goes the wrong way, then you first have this molecule with the metal ester, and then you make this active ester. And you make this from C60. So voila, the retrosynthesis of the stuff in the bottle. And the first step is to make what we call later on Pcbm. This is the rational design of the molecular electronic material Pcbm. Okay? I cannot be more honest with you then. So that's how smart we were. That's how lucky you can be. Okay, anyway, and then, believe it or not, it was mentioned already yesterday by Sean, indeed, these molecules, you can use the fullerenes not only as stuff for anti-HIV, but you can also put them in solar cells. But what do they do? In principle, in the solar cell, what does the fullerene do? It protects the polymer from oxidation. It's an antioxidant, if you wish, in the solar cell. And just as good as it can act as an antioxidant in the solar cell, it is oxidized in the solar cell. Degradation. You can use it as an antioxidant on your skin. Now, we don't use Pcbm because it forms a little bit of singlet oxygen, and I don't think that's a very good idea. By the way, vitamin E also produces singlet oxygen, so it's natural. But this one, this is an oxofullerene, this is a ketolactam derivative that we made, and this goes in this antioxidant treatment. Indeed, it's the same stuff. So 60 Pcbm, 70 Pcbm, as I showed this picture already. I don't need to stop there. 84 Pcbm. Yeah, it's a 350 millivolt better accepted than 60 Pcbm. So it's very interesting for N-type transistors, but don't ask me about the cost. So how do you make the materials for plastic solar cells? Oh, you can make them from oil, of just petrochemistry, just the normal petrochemistry. You can do combustion if you want to make fullerenes from that. You can use methane and then go aromatization, molybdenum and silurides at 700 degrees. So you go from natural gas, you can go to oil, and then you do your petrochemistry. And if you're really crazy, then we're going to make solar cells from CO2. So take CO2, you convert that to methanol, then there is a process that is aromatization, and then you can make your conducting polymers and your fullerenes, if you really wish. But you don't talk about energy payback time. But anyway, I mean, this is the last one is of course for fun, but oil and methane is normal. So this is how you can make fullerenes and how you complicate polymers. Fullerene production can be done on a very large scale. The Japanese have a so-called Frontier Carbon Corporation, and they have some patents. Mitsubishi Corporation mainly, and so they can make C60 or fullerenes on a very large scale. So that is by combustion synthesis. So you burn, for example, toluene or something. You burn it under very special conditions so that you get a lot of soot. And you collect the soot, and then of course you do an extraction to get the soluble fraction, which is the soluble mixed fullerenes, anywhere between C60 and C100, and then you have to purify and you get the pure fullerenes. That's how it's done. This is the one that we had already, but it's important to see that indeed this is with C60, and there are not many rates known between conjugated polymer and other acceptors, I must say. It's a little bit disappointing. So, photo-induced electron transfer, photo-induced hole transfer, they're all there. And then came the next thing, and it was also done with fullerenes. And the next thing, which was not so trivial at that time. For you, probably it's all known and very trivial, but I promise you, at that time it wasn't at all. And that is the idea that the VOC of such a device has to do something with the ingredients, and not simply with the different work function of the two electrodes. Because I was taught by my colleagues for a number of years how this solar cell worked. And it was as such that you have to use two different work function electrodes, because they give a big field and that does the separation. That was how that's how we explained for at least probably 5 years how this solar cell worked. And then of course we learned that there's much more, and it's not like that. But to prove that the VOC has something to do with the ingredients of the cell is of course very interesting for people who work with materials, because if the VOC is only determined by the electrodes, what fun for me? There's no fun in the whole game. Yeah? So what we did is we made fullerene derivative with different acceptor strengths. Yeah? So if you have a fullerene with different acceptor strengths, what does it mean? The LUMO goes down. If a stronger acceptor, then the LUMO is lower. If the LUMO is lower, then my VOC should be smaller. Right? So we made Pcbm, we had already this azafulleroid, we have C60, and we have this oxidized azafulleroid that you know that is in this skin cream, and so that is the same kind of molecule, but with a little bit less of a tail. And these three are quite soluble. Of course, C60 is not very soluble, so that was a little bit difficult. But then at that time, the only group in the world that made solar cells in Linz was in Linz. They made the solar cells with these four compounds, and they looked at the VOC and they found this kind of a relationship. This is the first reduction potential of the acceptor. That means how low is this LUMO. Yeah, the first reduction potential is less negative than the LUMO is lower. It's easier to reduce. And they found this relationship. The VOC was the highest with Pcbm, and it became lower and lower and lower until you get K+10 with a nice fit, with a linear fit. And so this was quite important. And in the beginning we said this homo-LUMO distance determines the VOC, which is of course nonsense. It does not determine the VOC. Let's say that's where the VOC is limited to. To start with, the amount of light determines the VOC. In the dark you have no VOC, and with a little bit of light you have some VOC. So it has nothing to do with these levels. Yeah, no, I mean, we have to be a little bit careful. But it's easy to let's say just work with the concept that this limits the VOC. And this has been used since then as the way to try to design the right materials combinations so that you have the optimum VOC and you have enough energy to have your charge transfer, enough energy to have your charge transfer, and still enough VOC. So this is how you can play with it. And the next thing is, of course, the thing from the beginning. Morphology. It's interesting to mix two materials and then to overcome the problem of the exciton diffusion. But of course the big problem is morphology, because you make a mess. How do you expect a mess to work? I think it was pretty lucky that this mess worked. And everybody from the very beginning said, we should get rid of this mess. And then it depends on to whom you talk to. If you talk to a polymer chemist, he says, I know the answer, di-block copolymers, and it will solve all your problems. You talk to a supramolecular chemist and say, oh, I know how to do that. That's easy. You just have to organize all the molecules and they will organize and you have everything in order. Okay, so this is what we spent about 6 years on. It was great. It was great fun. So these are the kind of, this drawing is probably about 14 years old. And the drawing means, wouldn't it be nice if we had the two electrodes, and then between the two electrodes we have blue and red material, donor acceptor obviously, and this only means electronic coupling, not physical coupling or not. This means electronically coupled to this electrode is the blue, and electronically coupled to this electrode is the red, so that we have this situation. And still, of course, this is a kind of a dream situation that we want to have this. Right? And then you can say, okay, now we can think about the thickness. The thickness has to be such that we absorb most of the light, but we don't want to make it thicker because then we have a problem with charge carrier transfer. The width of the domain, we know how wide it has to be. It has to do with the exciton diffusion length. And don't make it too small, because if you really make it very small, then you probably will get a lot of information. Voila! Now the question is how we make it. So we're going to make something which we dubbed the molecular electronic highway. Yeah, so you need to have these highways of fullerenes and lanes of polymer, and maybe we need something in between to not get too many collisions, recombination. Do we need something at the side? No. So we go from this random bulk heterojunction to this very dreamed ideal situation. And so what you do is you say, oh, how can we make bread? We can make like sheets. If you look from the top of the, or from the side of the layer, it could look like this. From the top, maybe you have a grid of acceptor in a kind of blue donor material, or you have pipes of one and another, or you have, or maybe you need a gradient, or whatever. You can think of all kinds of structures, but the problem is, how shall we make them? Right? And I would dare say that hundreds of people have tried all kinds of ways to make this stuff. Here's the di-block copolymer idea. So you have a block copolymer. So you have this is one polymer chain, and if this has a donor block and an acceptor block and a donor block, and this is all, then you hope that these molecules in your happy dreams, they would all stack on top of each other. And the next stack of polymer chains would sit also like that. And now we have a blue domain and a red domain standing up, which looks like this idea. And this is as old as the start. So in the smallest versions, you take two fullerenes and a little piece of a conjugated polymer. And you can vary the length of the conjugated polymer, and you can do a lot of photophysics. There's a René Janssen did all the photophysics of these molecular diodes. And still people are working on molecular diodes for several reasons, but we have learned in a very early stage that they are not ideal. Now because it's annoying. Okay, we'll be back. There you go. There's some kind of.
I thought you had it set for 45 minutes.
Yeah, but there's something you really don't hear. What is this? Yeah. Oh, it's this picture. Okay. There's something wrong with this picture. So if you want to limit the domain size, you can take a short molecule, let's say one fullerene, with a short piece of donor. And then if you cannot make large domains, if you have the fullerene bound to the donor, the domains cannot be larger than something like two of these next to each other, two of those next to each other, two of those next to each other. So you have very limited domain size. And what we learned is that the fill factor of those solar cells is never more than 0.25, which points to a very massive recombination. That's the problem. It doesn't work. And then we had the famous double cable principle. That is the idea of having a conjugated polymer. This looks like a molecular highway again. Eh? So you have, it's very simplistic. You have this polymer, which is the donor, and then the side groups that are the fullerenes. This would be the negative, the negative highway, positive highway. And those molecules were beautiful, and we could make them with a lot of work. It took more than a year of synthesis to make these molecules. Very complicated. The answer of that whole story, and I'm not going to show you the supramolecular approaches, we did many supramolecular approaches. The end of the story is very simple. The molecules became more and more beautiful. They were easier and easier to publish in England. They all loved those beautiful molecules. And the devices became worse and worse and worse and worse. But then we stopped. This is not the answer. So, very clear that if you look with Alison Walker's model on how fine or coarse should the mixture be, that there is some optimum for the materials at a certain grain size. That's where you have to be. And don't go there because you get recombination. Don't go there because you have the acetone diffusion problem. So somewhere, and of course it depends on the materials, somewhere there's this optimum. So it's much easier to do this in a very cheap and simple way as we do usually, and that is just by mixing two materials in a solution, spin coating, drop casting, whatever you like, and work until vary the parameters until you have something that works. Because it is a little bit of work, but then once you find the conditions, then you have them and it's okay. And it's for free. So, no supramolecular chemistry, no covalent donor acceptor systems, but work with materials that you control the crystallinity, solubility, kinetics of solidification, glass, precision, temperature, they're all important, and the compatibility between the materials, specific interactions or the similarity, or maybe you use an electronic soap or something else to make them compatible, and you think of something and you just mix. So, much easier. Take separate donor and acceptor materials, take compatible donor acceptor pairs, optimize the common solvent, do some annealing or not, slow evaporation or not, and you have to work a little bit on your lucky combo. This is the main recipe for now at the moment. And here are some simple experiments that I can show you. They're old, but they show the concept of the story. If you take MDMO, PPV, and Pcbm, and you dissolve them in toluene, that is not a good solvent for these materials. And if you spin coat that and you take an AFM picture of this material, then you see big blobs. Big blobs, way too big. This is not smooth. And the efficiency of the solar cell is less than 1%. If you do it from the chlorobenzene, which is exactly the optimum solvent for these molecules, it is not the solvent for OPV, as people then think. If it works in one case, it should work for every case. It's nonsense, of course. But the chlorobenzene for these two materials gave then the 2.5% cell. If you take PCHT and something like PCBM, but then with a thiophene group instead of the phenyl group, if you do fast growth from chloroform, then you get this kind of a fine structure. If you do a slow growth from a higher boiling solvent, you get much more interesting structure here than over there. If you do a slow growth from a real slow evaporating solvent like ODCB, then you get all this funny wire stuff. And then if you are here, you get the good activity. You get your efficiencies of something like 5%, and here you have an efficiency of, if you do not anneal, you have an efficiency of 1% or something like that. You can also play with the side chain of the PCBM. This is PCBM with methyl ester. You can also make PCBE, meaning they have an ethyl ester, or an isopropyl ester, or an ethyl hexyloxy ester, or an MDMO kind of ester. Or you can take out the phenyl group, or you can make this not butyric but propyl, or you can put substitute, and so on and so on. And by doing that, you can vary the solubility and the processability, and also the let's say the similarity with your polymers. And so if you, for example, look at PCBM and PCB-DMO with a very long chain, this is extremely soluble compared to PCBM. And so that I can show you the result. So if you use some kind of a PPV with PCBM from toluene, and I told you that toluene is not a good solvent for PCBM, you get, if you look with electron microscopy, and you see these big blobs of PCBM. If you use this now, the very soluble derivative instead of PCBM, under the same circumstances, you see that you already have a much better morphology. If you use the PCBM, now we go to chlorobenzene. This for chlorobenzene, this is it doesn't look very good, but remember, chlorobenzene and this PCBM is probably the optimum combination here. If you use chlorobenzene for this very soluble fullerene derivative, now you see that you have molecular dissolution, probably you have a molecular mixture. So it's a massive recombination situation. Not good. So you can choose, you can tune with solvent and side chain length. You can play and see and organize what you have. And you can play with the compatibility, of course. You can play with the compatibility with respect to electronics. So you can play, this one is a slightly stronger acceptor. This is a very strong acceptor. You can put side groups on the PCBM. This one was specially made for polythiophene, thinking that this thiophene has some similarity. And, oops, sorry. And the ones on the bottom were made for polymers that have these side groups. You have the polymers that have the fluorine, the dialkyl fluorine moieties in the polymer. You have them with C6, C8, and C10 tails. So we made these fullerene derivatives that they can mix with the different polymers. Of course, all of these derivatives, they are not the same with respect to electron transport and so on. There are all kinds of problems, or recombination. These are very apolar groups, so you have a lot of grease in your solar cell, which is not a very good idea, obviously. What is very important is the material's quality. And there, of course, with the fullerenes, since they are small molecules, we have a much better situation than with the polymers. With the fullerenes, they're commercial products. They have a constant quality. The impurities in the 60 and 70 PCBM is checked down to 5 ppm. There are certain compounds that you don't want to have in the PCBM, and the industry takes them out. Low molecular weight, constant molecular weight, no molecular weight distribution. It's a simple molecular. Now beware, 70 PCBM is a mixture of isomers. 3 isomers mainly, but a few smaller fractions are in there. And it's just too expensive, too crazy to separate them, so everybody works with the mixture, and it works. Surprisingly well, I must say. And following bis adducts, they are mixtures of isomers. I come to that. In contrast with polymers, we have lots of problems. The quality of the polymers is varying like crazy. And polymer chemistry of conjugated polymers is not as sophisticated as you would probably think. It looks good on paper. Everybody draws what you want to see, but that's not what you get. Okay? Everybody draws the structure of the stuff that you want to have, but they don't draw all the standard mistakes that you get from polymer chemistry. Don't forget, if you have a very high quality polymer with a molecular weight of a good polymer, a real good polymer has a molecular weight of 1 million. That's a real polymer. Yeah, like your plastic bags and stuff like that. And that's good polymer stuff. If you have a molecular weight of 1 million, and you have your building block has a molecular weight of 250, then you'll have, what is it, 40,000 units, and that means that you have 40,000 coupling reactions. You probably understand that the chance of getting 40,000 reactions to go well is not so big. And that works with the big industrial plastics, because thousands of people have worked tens of years on that and optimized everything. And here we go, and every group makes so-called conjugated polymers, and they just do it in a standard way, and I promise you, you get crap. What you work with in your work solar cells usually is kind of crap. For me, as an organic synthesis guy, it's crap. Because if I analyze it with mass spectroscopy, I see many, many times more peaks that I don't want to see than the peaks that I do want to see. Okay? Believe me, it's really horrible. So there's a lot to do in improving, although they got Nobel Prize for palladium catalyzed coupling. And the Nobel Prize was just given lately. But nevertheless, how important it is, it's beautiful, but still it's crap. Okay? So beware. If a chemist tells you I have a beautiful new polymer for you, it's simply not true. But since you don't have a choice, you have to work with it, right? But don't forget that it's crap. Okay? So this is something that we really have to work on, because it also has to do with stability. The more crap is in there, the more energetic disorder is in there, the more morphology disorder is there. So you have lower conductivity, you have shorter exciton diffusion length, you have shorter lifetime, you have recombination, you have traps, all the things that you know as a physicist, you get them for free from us. Okay. State of the art is with Fullerenes. That's why I had this title. It's with Fullerenes, of course. So 70 Pcbm. Yeah, 70 Pcbm. As I said, this is the absorption spectrum of 60 Pcbm. This is the absorption spectrum of 70 Pcbm. So clearly, if you make the right solar cell, this should help. Well, it does, because if you use MDMO PPV, and MDMO PPV, as I told you, is a lousy polymer for PV. It's just we had it. That's all. And it's a lousy absorber with a relatively wide band gap also. And if you now replace PCBM by 70 PCBM, you can see that the EQE spectrum, this is with 60, this is with 70 PCBM, you can really increase that. Really increase that. So this is how, after a lot of work, it took more than 1.5 years back then in order to get it finally to work in 2003. And if you use 70 PCBM with this MDMO PPV, you go from 2.5 to 3%. So what does it mean? That means that there is a whole transfer contribution. This means this can only be true if indeed the acceptor absorbs the light. You have maybe exciton diffusion in the acceptor to the interface, and you get a whole transfer. And indeed this is true. We have proven that later. We have also looked at the rate, compared that to the rate of electron transfer, which I told you is 40 femtoseconds. And last year we looked at the rate of the whole transfer, and it's even a little bit faster. It was something like 30 femtoseconds. So now the famous picture that you always see, that is this picture, that is light is falling on the polymer and you get an electron jumping to PCBM. This is the revised picture. You have to show both. Also, light is falling on the acceptor and the whole transfer is falling. And it's 30 femtoseconds. Up to it's already 2010. Sorry, but nevertheless, it's still true. So we have the electron transfer. We have the whole transfer. Then I'm almost done. We have something else, and that is since a few years you have some bis atoms. Maybe you have heard of ICBA or bis PCBM. And why do we have them? Because we had the wrong polymer. Because of it's P3HT's fault. P3HT is too strong of a donor. Yeah, that was a disadvantage of P3HT. So people say, oh, you guys, you made the wrong acceptor. So it's depending on from which side you look, right? So the polymer guy said, you have the wrong acceptor. So there's no other thing what you can do. You make an acceptor that goes with P3HT. So if you have a stronger donor, what do you have to make? You have a weaker acceptor. Otherwise you go too fast. So we have to make weaker acceptors. How do we make a weaker Fullerene acceptor? I showed you the stronger ones. When I showed you the VOC story and how it depends on the first reduction potential of the acceptor, we made stronger acceptors. Now that's of course not the way to go with P3HT, because then you have zero VOC. So we had to go the other way. So now it's very simple. One solution to the problem is very simple. There are other solutions, but they are more complicated, too expensive. But one simple solution that we tried and it works is, okay, look at C60 and then at PCBM. I tell you, I promise you, the first reduction potential of PCBM is 100 millivolts lower than of C60. It's 100 millivolts harder to reduce than C60. So that is when you put one group on. So the simplest thing you can do is that if I want to make it 100 millivolt more difficult, just simply put two groups on. And that was known, in principle that was known. So it was not so surprising, but anyway. So what we did is we take Pcbm, but now you don't make Pcbm with one side group, but Pcbm with two side groups. And this is called bis Pcbm, bis adduct. Now there's only one little problem. Nasty problem for the chemist, and I really hate it. That is, if you have this mono adduct and you put the next, I think, no, I don't have the picture here. I should have had the picture here. So the second group reacts with one of these 29 double bonds that you have there. And there's really not so much difference between the 29 double bonds in energy. They're all reactive. Well, the ones that are really close to this group, of course, they are blocked a little bit. But all the other ones, they can react. So if you look at the mixture of isomers that you get from this, and if this one is here, this one can be here, 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 here. And here, in one chromatogram, this is time. And this is time that it takes for all the isomers to come from a column. So every peak is an isomer of this Pcbm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 11, 11. All isomers of this Pcbm. This whole terrible mixture of isomers you can take. That's the good part. It's surprising that you can take this horrible mixture of isomers. And you do a cyclic photomegram. You reduce this whole mixture. And the first reduction potential, look at the red peak. It's not much wider than the blue peak of Pcbm. It's amazing because these things, they must have different reduction potential, but we don't see too much of that. So, but you can see that the red one is a little bit to the left of the blue one, and that's 100 millivolts difference in the cyclic photomegram. So again, the bis adduct is 100 millivolt harder to reduce than the mono adduct. So the LUMO of this one is 100 millielectron volt higher. So if you dream everything goes right, the solar cell should have a VOC which is 100 millivolt higher. So, but does this transport? How does it go? Well, this is the plot of charge. Space charge limited current determination of the mobility, and it's funny, the mobility in this case is roughly 7 times 10⁻⁴ centimeters squared per volt second, which is only a factor of, let's say, 30 less than Pcbm. So for the fact that you have such a horrible mixture, I think it's surprising that it's still working. After a lot of work, Martijn Leenes took the bis adduct finally to the situation with PCHD with a lot of variation to finally get what we hoped, and that is simply this. The blue curve is the IV curve for 60 Pcbm PCHD, and the red curve, you see the current is almost identical, but the VOC is 150 millivolt more. So there's even 50 more millivolt for free, which is interesting, but I'm not going to go into that. So this is exactly what you like to have. And there are many other derivatives of C60 that are being used in OPV. I don't have time to go into that. They're not so important. There are some this substituted methanolfullerenes, and there are some funny ones. There are the famous ICBA, for example. They are Diels-Alder adducts, and you have 70 C70 adducts, but they don't help really. They have not given, let's say, any specific advantage in their use. So, I think for now I have shown you enough Fullerenes, and I hope we have time for questions and comments for both sessions. Okay.
I would like to know about the shape of this that you have shown in the video.
Can you repeat the question, please?
About the shapes of C60.
Yeah.
You have shown that helium and dissolved in toluene.
You want the slide back? Here? Here?
Hier.
Next slide.
I don't, sorry, I'm not going to please help me.
He's asking for PEM image.
Transmission electromagnetic.
He asking for PEM image.
Oh! Of PCBM? Well, now we get to this interesting rocking picture. Okay, over that. Where is it? No. Wait a second. This? You mean these pictures?
Yes.
Yes.
Here. Yes.
One further?
No, this one.
Yeah?
You have shown some drawings of the C60 PCBM. Some soccer ball, something like
Yeah.
soccer shape. But here with this PCBM shows some different shape.
Ah! Okay. It's good that you ask. One of those black blobs is probably, it's about 400 nanometers thick, which means the diameter of this black blob is 400 PCBM molecules wide. Yeah, so this is not one molecule. No, this is crystallized PCBM. This is about a few million molecules in the blob. Okay?
Yes.
So therefore the shapes are all different, of course.
You told us how you synthesized PCBM, but how did you figure out that it was useful for OPV?
How did you get?
How did you find out it was useful?
Yeah. Sela Sadicivci and Alan Heger had discovered that when you take this acceptor of Udall, C60, and you add it, that you get photoreduced electron transfer. Now you want to make a bulk heterojunction. The story is, by the way, that a Dutch polymer physicist who also worked in Santa Barbara told them about the idea of interpenetrating networks in polymers. So that if you use two polymers, that you get bicontinuous interpenetrating networks, and that may be a good idea. That's the story, an interesting story. Now, they didn't use two polymers, but they wanted to use C60 because they just discovered that this worked with C60, so the polymer and C60. So they were making somebody in the group of Alan Heger was making the first solar cells, trying to make some kind of a bulk heterojunction with the C60. And what did they get? These big blobs. They got big crystals of C60 because C60 really does not want to mix with a polymer. It wants to crystallize. And you can probably imagine that a ball, the shape of a ball molecule really knows how to crystallize. Yeah, that's very easy. Yeah? Every time the molecule is close to the crystal, pop, it fits. You know, every collision is right. Yeah? You know what I mean? So C60 was not a good idea. And we had a little meeting to increase the collaboration between the chemistry group of Woodall and the physics group of Heger, because you have to always maintain, it's like a marriage, you have to maintain the marriage. And so we had this meeting, and Fred said to us, René Janssen was working with Ellen, and I was working with Fred, and said, well, you're both Dutch, so you, Dutch Mafia, you organize this meeting again. So we said, okay, and then we're going to talk about our problems. So the physicist came and said, we want to make a bulk heterojunction solar cell with the C60, and it doesn't work. Why? Well, the C60 crystallizes. Okay, I have maybe a compound that I use to make HIV, but this is very soluble. And it's probably soluble in the same kind of solvent as you have for the polymer. So why don't you use my molecule? It wasn't called PCBM. Why don't you use that stuff? And voila, boom, bingo. That was the story.
One more quick question. You're
Thank
gonna
you.
fire it out.
Thank you for your nice presentation. You mentioned that your dream was that column, that very well arranged columns that you try to reach them. And also you mentioned that the purity is very important. So I would like to know what do you think or what do you predict would be the future trend on these OPV?
Oh, I'll tell you tomorrow. Come back tomorrow.
Okay, there's coffee and cookies out there, and I think you can probably ask questions informally during the break. That's what it's for. And we'll come back here about 3:30.